Hello and welcome. Check out that old reassuring blank wall behind me. It's good to be back. Today I'll be discussing an addition I made to the MAME source debugging feature preview. If you don't know what I mean by the MAME source debugging feature preview, check out this video on the MAME source debugging feature preview. Special thanks to Glenn Hewlett for pointing out his scenario of using the Coco 3's memory management unit to swap code in and out of the same logical address range. If you don't know what the Coco 3's memory management unit is, or what I mean by logical address range, don't touch that dial. I'll catch you up. Today we'll explore the madness that ensues when you enable source debugging in MAME and make aggressive use of the MMU. We'll review how the MMU can be used to swap code or other data in and out. We'll explore a way to use lwasm and lwlink to create apps that exploit the full extent of your Coco 3's physical RAM, even as it exceeds the 64K of addresses available to your CPU. We'll then go over the additions I made to the unofficial builds of lwtools and MAME up on my preview repo, how you can make use of those additions and explicitly tell MAME how the MMU is affecting which code is getting executed, and finally how to script it all with Lua so the debugger automatically adapts as your code executes. And along the way, maybe we'll learn a little something about ourselves. To demonstrate the problem, we're going to step through some code. This is based on some example code that Glenn sent me. So we start off loading U at the value of 3333. Whoa! What just happened? U didn't even change, but somehow we moved to a completely different source file. Okay, so I guess we're here now. We'll store A into this location. We'll load A with 1. A is 1. Okay, so we're fine now. We'll store A back in that location. We'll load A with 2. Whoa! What's this? Where are we now? Crazy stuff is happening. If I keep stepping, I keep just wildly going into other places. Back and forth, back and forth. Why? Well, if you read the title to this video, you know it has something to do with the memory management unit. But if you're paying close attention, you'll see that we're executing code that is barely even touching the MMU, and yet somehow we are wildly jumping from source file to source file without warning. And it's clearly not what's really getting executed. So if I open up the disassembly, we are not matching. Are we loading a U? Are we loading an X? Well, X is the one that changed. The disassembly is working just fine. And if we keep on moving, all of a sudden, the source file changed, but nothing has changed about our disassembly. We should be doing some no-ops now. It seems like the source file caught up, but now it's back due to some other crazy place again. Now, as a reminder, in order to get source-level debugging to work, you have to give MAME the path to a MAME debugging information file. So this is what got generated when I built this program using lwasm and lwlink. If we dump this out, then we'll start to get a clue. So this app consists of 4 different source files, and let's see how the binary addresses map to those source files. So address 2000 goes to source file number 1, line 24, so that's going to be here. But if we scroll down, 2000 also maps to that same source file, line 4. And if we go down a bit further, 2000 also maps to source file index 2, line 5, which is this source file. Now, why would the same binary address map to multiple lines of multiple files? Well, that's where the whole memory management unit kicks in. This app that we're stepping through deliberately loads different blocks of code to the same logical memory addresses. And even in those times when we're not actually swapping code in and out of those logical addresses, lwlink still has told us that all of those blocks of code map to addresses starting at 2000. So even when code isn't getting swapped in and out, some other debugger needs to know which source file is actually active right now. And it's got a bunch of inconsistent information. So let's take a step back and see what's actually supposed to happen. We're supposed to start here. I call this block A because we just play with the A register. We load it with values, we store it somewhere, load it with values, store it somewhere, blah, blah, blah. And then we write to the memory management unit. This is now changing where logical address 2000 is supposed to point. And it's supposed to be pointing now at this code, which plays with the B register, does a bunch of B kind of stuff, and then it writes to the memory management unit to load in some other code, this time a block of code that plays with the X register. So let's take a quick detour into the Coco 3's memory management unit. I do have an earlier video that goes into much more detail about how this works, but you don't need to watch that for now. I'll summarize what you need to know. But if this leaves you curious to learn more, there is a link in the description. The fundamental problem that's solved by the Coco 3's MMU is the fact that the 6809 can only directly address 64 K's worth of memory. So that's going to give you 4 hexadecimal digits of addresses. But you can actually expand the Coco 3 to up to 2 megs of physical RAM. So the memory management unit allows us to redirect any reads or writes to those 64K worth of addresses to anywhere in physical RAM. And it does this by dividing up those 64K logical addresses into 8 different blocks. Each block has 8K worth of addresses. 8 times 8K gives us these 64K of logical addresses. And by writing to these special hardware registers on the MMU, we can control how the memory management unit redirects reads and writes to each of these blocks to the physical RAM. We just take whatever value, for example, is stored at FFA0, multiply that by hex 2000, and that gives us the beginning address in physical RAM where this 8K block of logical memory addresses will point. Similarly, for the next block, we use FFA1 and its value times hex 2000 to decide where in physical RAM this will point. As a simplification, I'm only talking about the executive set of registers. There is another 8 hardware registers called the task set that I'm not going to be concerned with for this. So in this sample code, I'm specifically concerned with this 8K block here, the one starting at hex 2000. I can point it to the very beginning of physical RAM, I can point it to the very end of physical RAM, I could point it to somewhere in the middle, I can point it wherever I want, simply by changing the value of the register at FFA1. And so what the app does is, on startup, this block will point to this code, the A block. And then once we get down to here, and I write a new value into FFA1, suddenly that block gets swapped out, and now I'm in the B block. And then once I get here and write a new value to FFA1, I'm suddenly going to be in the X block, and so on. Now the assembler and linker don't really know anything about the MMU. They just simply expect you to express everything in terms of logical addresses. So how do we get the assembler linker to do our bidding? How do we get it to know that all these different blocks need to be assembled to the exact same address? And when we go and load the binary, how do we ensure that each of these different blocks gets stored in the correct physical addresses? Again, thanks to Glenn, I learned about some kind of cool tricks you can do with lwasm. To start with, all of our blocks of code get assembled to their own OBJ files here. That includes block A, block B, and just for fun, block X and U live in the same assembly file. But there's also one more assembly file here. This is some cryptic looking stuff, but this is pivotal to make sure that everything gets loaded properly. So we're going to come back to this in a second. The key to putting this all together is the linker. And the linker gets all of its directives here from the linker script. The linker script will tell it how to merge all of the binaries from the OBJ files we generated above into the final binary. The linker script allows you to use a section directive to tell it which block of code to place next in the binary. So we're going to start off placing the block called MMU-03 at address FFA1. MMU-03 simply has that one value. So this is the equivalent of poking 3 into address FFA1. And of course, FFA1 is that special MMU hardware register that decides where this 8K block of logical addresses will point in physical RAM. So in the binary, we're going to have a preamble that Radio Shack DOS understands that tells it, let's first load this first block to A1, FFA1, and that block is simply this single byte. Let's poke 3 into FFA1. When we're done with that, then we're going to take block U and we're going to put that at address 2000. Block U is the name of a section, so we need to have a section directive inside the assembly file that tells lwtools what we're referring to. So this line here says to place all of this code between the section and the end section into logical address 2000. But here's the key. Logical address 2000 is going to be pointing wherever we poked FFA1 to be. And we poked FFA1 with a 3. So 3 times hex 2000 will be hex 6000. So all of this code will really end up in physical RAM starting at hex 6000. Then we just do the same thing for the next block. For the next block, we have a single poke, this time the value of 2 into FFA1, so that we can then load the next block still at logical address 2000, but now logical address 2000 is pointing to hex 4000 in physical RAM. And in this case, the code we're going to be putting there is block X, which is up here. And we do it again. This time we poke 1 into FFA1, and then stick block B to wherever logical address 2000 is pointing now. And block B is this code. Finally, one last poke, this time 0 into FFA1, and then we can load block A to where hex 2000 is pointing now. And this is block A. Now, since this is the last poke we did to the MMU register, by the time the loadm command is finished inside Radio Shack DOS, the MMU is left still pointing at block A. So this is where we're going to start executing our code once we run exec. And this sets the postamble to say that the entry point is going to be wherever start A is. And start A is right here, pointing to hex address, logical address 2000, which is where our block starts. So what we should be doing when we execute this is execute through block A, boop, 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 boop. And then as we're executing, we're going to change the MMU to move to the address where block B starts. Once we do that, we're going to be here, but we're going to be here in block B. So that's going to take us to the bottom of block B, which lets us branch back up to the top of block B and execute all of block B. And once we get here, we're going to change the MMU to point to block X. Once we do that, we're going to be here at the bottom of block X, ready to branch up to the top so we can execute all of block X. And then one last write to the MMU moves us into block U, which will land us right here at the bottom. So we can branch up to the top, execute all of block U, and finally return back to basic. That's what should be happening. This is the order of the source code that we should be seeing in the debugger, but of course we're not, because the debugger has no idea that we're doing this. It has no idea that the memory management unit is being written to, and that the different blocks should be coming and going at specific times. Instead, the debugger just has this dizzying array of inconsistent mappings that tell it that the same addresses in that 8K block starting at 2000 map to completely different source files and completely different lines. We need to be able to tell the debugger when and how the memory management unit writes are going to affect the code that we're executing. So let's talk about the changes that I made both to MAME and to lwtools to get this to work. The change requires that you use lwtools sections so that any overlapping code can be uniquely identified by its section name. It isn't really strictly necessary to do this in general, but I'm using this pre-existing section directive so that you can help identify to the debugger which blocks of code are going to be swapped in and out and when. So as you've already seen, we have a separate section for block A, block B, block X, and block U. By doing this, we're going to get separate MAME debugging information files for each section. So let's go ahead and build this piece by piece to see what gets generated. To start with, in this directory, we just have some ASM files, some scripts, and that's it. Let's do the first line. That gives us the list file for block A, the obj file for block A, and importantly, it gives us the MAME debugging information file for block A. Now let's assemble block B. Just as before, we now have our output files for block B. The next file happens to have both sections for block X and block U in it. So by running that one command, we now have MDI file for block U and an MDI file for block X. Next, we assemble the MMU file. This isn't going to help with debugging. This just sets things up so that as we load everything, they get loaded into the correct physical addresses. But these MDI files are useless because we're not going to be debugging these single bytes. Now finally, we're going to link everything together. So far, nothing has changed in lwtools as a result of this new feature, but this line is going to show us something new. I'm asking it to generate the block's full MAME debugging information file, but it's going to be generating more than just that. It's also going to be generating new MDI files for each individual block, with the word relocated in the name. The difference between this and this is that the original MDI file was generated by lwasm, and it doesn't know where those addresses are going to be. All of the logical addresses start at 0. Because we're just assembling to an obj file, there are no addresses. In contrast, this is generated by the linker, and the linker is told where each section is supposed to start in the logical address space. So the linker can generate this and know that block A actually starts at logical address 2000. Block B actually starts at logical address 2000. Block X starts at hex 2000. Block U starts at logical address 2000. So these relocated MDI files are new, and we're going to use them in a new addition I added to the source debugging feature, where you can tell MAME to load multiple MDI files instead of just a single one. So now let's look at the MAME command line. Now that I have all of the overlapping regions of code separated out into different MDI files, I am no longer going to ask MAME to load this merged MDI file. Instead, I will ask it to load the individual MDI files for each of the blocks, block A, block B, block X, and block U. In particular, the relocated versions. So these are all the ones that start at hex address 2000 in the logical address space. By separating it out into different MDI files, I can then tell MAME to turn them on and off at the correct times. Just as an aside, if you've done any programming on Windows, and you've dealt with PDB files, if you say had a DLL that you dynamically loaded and then unloaded, and then another DLL that you dynamically loaded and unloaded, and if by chance those DLLs ended up getting loaded into the same virtual addresses, the debugger would have no problem with that because each DLL would have its own PDB file. And the debugger would know as DLLs get loaded and unloaded to use the PDB files for the DLLs that are still in memory. This is a very similar idea, it's just a bit more manual. The debugger doesn't get to know when stuff gets loaded in and out or switched in and out, so we have to tell it. So we give it all of the debugging information files we have at the beginning, and then we switch them on and off as we debug it. So let's see how that works. On startup, things look pretty much the same. If I show the source, I still have a choice of all of my different source files. But I now have a command I can use to view all of the source debugging information files that we asked to be loaded. So I see individual ones for the block A, block B, block X, and block U. And since I know that we're supposed to be doing block A first, I can go ahead and disable 1 through 3. So now if I list them out, I'll see that 1 through 3 are disabled, 0 is still enabled. And if I go up here, I'll see I only have access to block A. This is the only one that's loaded. So I'm going to go ahead and set a breakpoint at the beginning. So now my source code and my disassembly agree with each other, at least at first. And if I start stepping through, I should stay in block A all the way through all of this, because it's the only block the debugger knows about. Now I'm about to write to the MMU and change things. So I'm going to do that. You're going to notice that the disassembly will note a change because all of a sudden new bytes have gotten loaded up into that 8K logical address space, but the source file will not know. Step. So now you'll see we're located at the bottom of block B, but in the source code we're still sitting at block A because that's the only block the debugger knows about. But since I know better, I can go ahead and disable 0, but re-enable 1, leaving the rest of everything disabled. If I view my source debugging information now, we'll see that only the debugging information file number 1 is enabled. And sure enough, we're sitting at the bottom of block B, ready to branch up to the top and execute it. And that agrees with what the disassembly says. So we'll step through that. Everybody agrees, everybody is happy. And by the way, you'll see this is the only block we even have access to. So we're about to write to the MMU. So we're going to see that the block is going to change here in the disassembly. We're now looking at the bottom of block X, still looking at block B. So we just need to tell the debugger we're done with 1. We need to enable 2. Now we're at the bottom of block X. We can go up to the top, execute block X, and move on to block U. Disassembly knows, source does not, but we can fix that. Now we're at the bottom of block U. We can then branch up to the top, execute it, and then finally return back to basic. If you know your code well, this isn't too big of a deal to do, but wouldn't it be nice if you could automate this? Wouldn't it be nice if we could just tell the debugger to understand the MMU and to know that when we reach certain instructions and the MMU gets written to in certain ways to then do this SD enable, SD disable commands for us? Well, automating things like this is exactly why Lua exists. So I'm going to add to my command line a request to load this special script. We'll talk about this in a minute, but let's see what the effect of this is. Immediately on load, we can see that something is different. We already have these commands that were already run for us. And if I go ahead and list out the debugging information files, it already knows only block A should be available. So if I ask to view the source, only block A is there. So let's set a breakpoint and run. So we're here in block A. Let's step through as usual. Everything seems okay. We're about to write to the MMU. Let's just step. And poof! All of a sudden, not only the disassembly, but also the source and lockstep have moved us over to block B. And if I check my list, only block B is available. So now I can branch up to the top of block B, execute it. Now I'm about to move on to block X, step. And now I'm at block X. Go to the top of block X. Boom! Block U. Go up to the top of block U. And finally I can return. And if you've been looking down here, you'll see all of those SD enables and SD disables happened on our behalf. Now the Lua script really isn't that big. It's only about 100 lines or so. And most of that you can ignore. When you customize the script, there are only really a few places to change. The first place is what the initial state should be. And this simply says which MAME debugging information files we're going to enable and disable. In this case, we only have 4 files, and these are ordered in the same order that you would see when you run the sdlist command. So in this case, they're ordered by block A, block B, block X, block U. And this says we'll enable the first one, block A, and we'll just disable the other ones. And then as the code executes, we have a function that gets called every time the MMU state changes. So there's a table that's basically a set of if-thens. If the new MMU state looks like this, then enable and disable the MDI files like that. If instead the state looks like this, enable and disable like that, and so on. So how do you read this? These are the 8 different MMU registers. And this is saying if that second register, FFA1, has a value of 0, then regardless of the values of everything else, consider this condition to be met, and therefore do this action, which says let's enable the very first MDI file and disable the rest. However, if that second register isn't 0, but is 1, then go ahead and enable the second MDI file and disable the rest. If that second register is set to 2, then enable that third MDI file and disable the rest. And finally, if it's 3, only enable the last one. Why 0, 1, 2, 3? Because we know our code, and we know those are the values that we are setting in FFA1 as we swap code in and out. So if your code were doing something different, if it were setting different values into different registers, you would simply change these parts of the table to indicate what values and what registers you would consider for that condition. And then you would change which MDI files you want to enable or disable. But that's really all you would have to do. The rest of the script can just sit as is. And the rest of the script isn't much anyway. It uses the install write tap to get triggered whenever memory is written in a certain range. And in this case, we have the executive set from FFA0 through FFAF. And also, if someone were to switch between the executive set and the task set using the register at FF91, we would also run the same function here. And all this function does is it sets this table, which is what you customize, and then it just iterates through the table doing the if-then. If the state matches, then go ahead and enable and disable as those 1s and 0s say. If you're curious to learn more, you can read through all the code yourself. This script, as well as the entire sample app, are up on the preview GitHub, and there's a link in the description to find everything. Now that you're fired up and ready to improve your experience debugging that awesome MMU intensive app of yours, go ahead and check out the links in the description to the MAME source debugging preview repo and download the latest releases. They're free. These latest editions are not part of the original pull request that I opened against MAME, but if that pull request gets merged, this will be next on my list. As always, thank you for watching.